So our project is based on basically dynamic programming. Let me explain to you what it means. So dynamic programming is mainly an optimization over plain recursion. So where we see a recursive solution that has repeated calls for same inputs, we can optimize it using dynamic programming. So what it does is that the idea is to simply store the results of subproblems so that we do not have to recompute them at a later stage or when needed later. This simple optimization reduces time complexities from exponential to polynomial. For example, let's suppose there's a Fibonacci sequence that we have to get and we get exponential time complexity. But if you optimize it using dynamic programming, then we can sort it down to storing solutions of subproblems, and then the time complexity reduces linear. For example, a Fibonacci of let's say n can be distributed into a Fibonacci of n minus 1 plus a Fibonacci of n minus 2, provided that n is greater than 1. Hello, so my name is SUBHRANGSU BOSE, and in this project we would like to talk about the bin packing problem and an approach towards finding a near optimal solution with regard in comparison to the previously existing solutions. So in this project we apply the method of dynamic programming, that's a common data structure concept, to find a near optimal solution for the bin packing problem. So next question will be, what is bin packing problem? So the bin packing problem is an important problem which requires the sorting of items of a certain volume into bins or a certain volume while minimizing the number of bins used in the packing. The optimization technique applied to the problem is a very powerful technique and finds the solution of the bin packing. So what happens here is objects of different volumes must be packed into a finite number of bins or containers, each of volume V, in a way that minimizes the number of bins used. In a computational complexity problem, it is a combinatorial NP-hard problem, right? And usually NP-hard problems are associated with exponential time complexities, which is evident in our findings or recent findings that have been done in this regard. So an example of usage of bin packing would be loading trucks, creating backups, and technology mapping in FPGA chip and job scheduling. So usually to solve this kind of problem, there's a class of algorithms known as heuristic algorithms to produce a near optimum solution, because a polynomial time algorithm does not produce an optimal solution. So the purpose of our project is to create a solution and its implementation to prove the efficiency of using DP to create subproblems or divide a problem into subsequent subproblems and hence apply it in our work. So our approach in this regard would be that to compare the efficiencies and drawbacks of two most famous heuristic algorithms, that is the next fit and the first fit, and in comparison to those create a new algorithm that is a near optimal solution to the bin packing problem, right? And so the main concept we use is dynamic programming, so which is an algorithmic technique for solving an optimization problem by breaking it down into simpler subproblems and utilizing the fact that the optimal solution to the overall problem depends upon the optimal solution of its subproblems. Hence DP is used here. So an existing method would be, as we have already discussed, that given, suppose there are n items of different weights and bins, each of capacity C, assign each item to a bin such that number of total used bins is minimized. It may be assumed that all items have weights smaller than bin capacity. Now, with regards to this finding, this problem creates an NP-hard problem, and finding an exact minimum number of bins takes exponential time. Our aim or objective is to reduce this using dynamic programming. So our approach would be, as already mentioned, using a class of heuristic algorithms and using specific algorithms such as the first fit and the next fit, and comparing their spatial and time complexities, and hence move on from that and brainstorm subsequent methods to create a near optimal solution. Now my friend Souvik will explain to you about the implementation details or the different modules attached to our project, and describe briefly about the first fit, the next fit, and the near optimal solution, which we have coded in Python.
Hello, good morning. I am Souvik Mukherjee, and today I will be explaining about the coding part of our project. Our project work is on DSA, Data Structure and Algorithm, CSE 2003. I belong from VIT University Vellore, and I will be explaining about the coding part of our problem, the bin packing problem. The problem is a very important problem which is faced by companies like Flipkart, Amazon, etc. So we have basically used Python programming to solve the problem, and we have used three codes. The first one being next fit, second one being the first fit, and the third code we have developed one is the most optimum code, and that is called the best fit. So in our first situation, the programming takes the weight and puts it in a bin. It goes on taking weight and goes on putting it in a bin. Once a bin is full, it takes a new bin and starts putting it in the new bin. So this is the basic algorithm of the first programming, which is the next fit algorithm. So if you look on to our second code, that is the first fit algorithm. In our first fit algorithm, what we do basically is we take our input in a list form, we go on putting it in a bin. If a bin is full, we take a new bin, same as the next fit. But once we are putting it in a new bin, we again start seeing from the first bin and see if any bin is empty enough to take the weight which we are going to put. If it is possible to do so, we will put that in that bin. So now in this situation, it goes on checking from the first bin to n number of bins which we have used till now, and it puts the weight in the first bin where it finds it appropriate to fit. It does not see the number of space left out if we fit a weight in that bin. Now suppose example we have a weight of 4 and we have bins of capacity 6, 5 and 4. Left out capacity 6, 5 and 4. That is, the space left in the first bin is 6, second is 5 and the third one is 4. Now we have a weight of 4. In our algorithm of next fit, once we take the weight, we will start checking from the first bin. So in first bin we already have space left 6, so the weight could be put here. So the first fit algorithm will put the weight in the first bin itself. It will not check the second and the third bin. So this code is optimum in time complexity because it will fit the weight and it will leave, the code will get terminated there. But in the third programming which we have developed, it will see that the weight gets fit in the best possible way, that is in the third bin which we have said now. So the weight which we have is 4 and the bin number 3 is having space left 4. So we have introduced just one extra thing from the first fit algorithm, that is a minimum variable. This minimum variable counts the amount of space that will be left away when we put the weight in the bin. It will iterate throughout the number of bins which we have, and it will see that the weight gets fit in best possible way. That is the minimum value. The minimum variable has minimum value. That is, suppose in our example which we are giving right now, we had a weight of 4, bins of capacity left 6, 5 and 4. So our minimum variable in the first bin will be 6 minus 4, that is 2. Second one will be 1 and the third one will be 0. So in this situation, the loop will run for a longer time, but it will take the third bin as its priority because it is having least number of space after the weight is filled inside this bin. So according to our most best algorithm, or the most optimum algorithm, or the third algorithm which we have developed, uh, this weight will be best fit in the third bin. So in this situation, if we compare the same scenario with the first fit algorithm, the time complexity is more because the loop will get terminated once it will have a space to fit the weight in the case of first fit. But in our case of best fit, it will go on iterating until it finds a best fit. So in this case, it will run the entire loop and it will see where the minimum value is lowest. If found the lowest value, it will fill the weight in that bin, and if not possible, it will take a new bin. So that is what the third code is. It is almost similar to the first fit algorithm. Only the extra part we have introduced here is the minimum variable. It will just see that the weight is filled in a best possible way. So these were the three codes which we have developed, and now further we are working on variable bin problem. That is, in real life scenario, we won't have bins of similar weight which we have a similar weight capacity, like which we have taken an example. For example, we have taken a bin capacity of 10, so all the weight we put will be put checking the bin capacity of 10. But in real life scenario, we will have variable weight, so we have to check on that thing. And also we are looking forward to see problems based on volume, that is weights containing the height, weight and height, breadth and length. So checking the volume, that the volume gets fitted in a bin in the best possible way. So many companies like Amazon, Flipkart uses these algorithms to see that the weights get fitted in a bin in a best possible way. So not in a bin exactly, the packages which we receive, the algorithm in Amazon, Flipkart checks that the product which they are sending gets fitted in the package perfectly, that the package is not partially filled and is not empty. So this is basically an useful algorithm. Thank you.
Now, as we have mentioned already in our report, we have stated some findings. So these findings would be using algorithm 1, 2 and 3 respectively, that is the next fit, the first fit and the near optimal solution. As we can clearly see, for n less than 10, that would be, so number of bins less than, number of items less than 10, the algorithm 1 has a lesser execution time than algorithm 2, but the algorithm 3 records the least one. Similarly, for n greater than 10 also, algorithm 3 works in the least amount of time. And hence, comparing and analyzing, we have found that not only algorithm 3, that is the near optimal solution, works for matching the fastest speed, but also reduces spatial complexity and ensures a homogeneous distribution of items. Right? Hence, it is clearly evident that the solution that has been found here manages all three factors better than the previously existing algorithms. Right? So we conclude by saying that we have considered algorithms that have been used, which are comparatively contemporary, but we couldn't have come to a better solution than creating a new algorithmic approach, now which is the near optimal solution. While we sufficiently support the near optimal solution which is covered, that you can clearly see with our findings, we have continued to brainstorm on potential solutions that can be considered later on. One such optimization would include a bin packing facility with variable bin sizes that would significantly reduce any complexities. Another would be a system of bin packing governed not by weights of items but by their volumes. Hence, we can continue to brainstorm and carry on our research, because bin packing problem is one of the most complex problems, but a solution is imminent with the number of researches being carried on